Howdy. Most of this video will be spent working one-dimensional kinematics problems with an emphasis on the topics covered in the previous lecture video. That was the relationship between velocity and acceleration and position when we're talking about the integral side of it, the area under the various curves. But let's first take a look at a video that's linked on Canvas showing one of these Tesla vehicles racing some Dodge Demons. So this will be brief, but as they cross the finish line, I will pause so that you can take a look at the time it takes each vehicle to complete the race and their final speed. Okay, so the Tesla obviously won the race there because it finished first. But if you take a careful look here, presumably this marquee is for the Tesla and this one over here is for the Dodge. This would be the time of crossing the finish line. So the Tesla finished, what is that, something like 0.3 seconds before the Dodge. It finished at 10.8 seconds, and the Dodge finished at, okay, more like 0.4 seconds because it looks like it finished around 11.2 seconds if you round to the nearest tenth of a second. And yet, look at the final speeds here. They don't give units, but I think we can assume it's miles per hour. My Corolla does not go 125 miles per hour. Not that I've tried, but I just suspect that it's not capable of that. So look at that. The Dodge finished later, and yet it had a higher maximum speed, or a higher final speed. Now, if you've been getting a lot of practice with these constant acceleration kinematics problems, that may seem like a contradiction to you. If you were doing a problem where the two vehicles each had their own constant acceleration, you would find that whichever car finished first was also going faster at the finish line. And yet here we have something different. The car that finished first actually had a lower speed when it crossed the finish line than the other car did. So the answer is that these cars do not have constant acceleration. I'll throw up a graphic here with a totally exaggerated interpretation perhaps of what's going on. So let's just pretend that these two curves, let me grab the laser pointer, that these two curves on a velocity versus time plot show how each vehicle's velocity depends on time. And you'll notice that the Tesla has a steadily increasing velocity. Now, what can you get by looking at the slope of velocity versus time? The slope, we know, is the derivative. So the instantaneous rate of change of velocity with respect to time is acceleration. You can see there's a positive constant acceleration. Now, I'm sure that Tesla's acceleration was not, in fact, constant, but I'm just picking an exaggerated behavior for the two vehicles to demonstrate the concept here. The Dodge, on the other hand, has a very low acceleration at first. I know that because look at the slope here. The initial slope is less than the constant slope of the Tesla's velocity versus time. But after it's been going for a few seconds, the acceleration kicks in. I almost said kicks in a gear, but I don't want you to interpret that literally when it comes to gear ratios. And here you can see why this graph is really unrealistic. I just grabbed a plot off the web. This is an actual exponential function. No car is capable of having a velocity that increases exponentially. But at least the difference between the Dodge acceleration here and the Tesla acceleration will enable us to understand how the Tesla could finish first despite having a lower final speed. So finish first. When you finish, that means you've completed the displacement necessary to get to the finish line. How does displacement relate to this graph? We're looking at a graph of velocity versus time. And let's suppose that the Tesla reaches the finish line at this time. This is T Tesla final. And we can see from the graph that it would have this velocity, V Tesla final. And I will remind you now that if you look at the area under the velocity curve between the starting times and the finish times, or the starting and finish times, that will give you displacement. So the area of this triangle is numerically equal to the displacement. In other words, the length of the racetrack. The Dodge, you can see if you were to evaluate the area under the Dodge velocity curve up to that same time, and I wasn't able to shade that in because it's an awkward shape. I don't have that shape in PowerPoint, but look at the area under this exponential curve from 0 to t Tesla final. I think it's safe to say that that area is less than the area of the triangle. So at this time, the Dodge's displacement is not yet equal to whatever the Tesla's displacement was. Let's just call it 400 meters. So the Dodge is going to have to drive for longer. Maybe when we get to this time, t Dodge final, the area under this aqua curve is now equal to the area of the triangle up to here. All right? So because the curve is kind of flattened at first and then it rises, we've got to take the area under the curve for a greater time interval before we get to that same displacement. In other words, before the Dodge gets to the finish line. And you'll notice at that time, the velocity of the Dodge is in fact greater than the Tesla's velocity was when the Tesla crossed the finish line. So the resolution of this conundrum, if it seems like a conundrum to you, is simply that the acceleration is non-constant, at least for one of the vehicles. And again, neither of these v versus t curves is accurate. I seriously doubt the Dodge's velocity looks like this, but it's a demonstration of concept at least. Let's take a look now at one of the simpler problems from your Chapter 2 homework. They give you a plot of some particle or cars or rockets, velocity versus time. One of these days I'll remember to get the laser pointer before I hit record. So we see that the velocity increases and then decreases before going negative. And we're supposed to figure out at what time does this particle wind up at the coordinate x equals 35 meters. So we know how fast it's going and in which direction in meters per second. That's the information given in the graph. And we're also told, I should have put this up, but we're told that the particle starts at the origin at t equals 0. Let me add that into the slide. I could have written x sub 0, x naught equals 0, but remember the sub 0 is really just a label. It doesn't have to correspond to 0 seconds. So I'm emphasizing that at the 0 second mark, the x coordinate really is 0 meters. How do we proceed? How are we supposed to turn information about the velocity into information about the position? Well, remember, position, if you take the derivative of position, dx dt gives you velocity. So it's easy to go from position to velocity. You take the derivative. If you want to go from velocity back to position, you would need to take the antiderivative, and hopefully at that point you remember, aha, the area under the velocity versus time curve between any two times will give you the displacement over that time interval. That's all we have to do. So if you look at this equation, provided you can calculate this integral either by using algebra and the power rule, etc., the rules of calculus, or geometrically, see here we could just look at the picture and figure out the area by using areas of triangles and squares. Provided you can calculate this area and provided you know what the x-coordinate is initially, you can find the x-coordinate at that time. This is one equation, right? So there can only be one unknown in this equation. So maybe you want to put the x initial on the other side and write it this way. Plug in the initial coordinate, plug in the area between the two times. That will give you the position at the end. In this case, the initial coordinate at t0 is 0. So look here, I'm evaluating the initial time to be 0. That's how the problem is written. It doesn't have to be 0. They could tell you what the initial position was at t equals 5 seconds. Then you would just plug whatever that position is here, and you would plug in the number 5 here. So when is the x-coordinate equal to 35? So basically, we just want to find out at what value on the t-axis does this integral have a value of 35? Because if the area is 35 and we add it to 0, then we will have the number 35. As time advances, you see that the velocity in here, actually this entire time, the velocity between 0 seconds and 8 seconds is positive. So down here, if this is your particle, for those first 8 seconds, your particle is moving to the right the entire time. What does the height of the curve tell us here? How fast the particle is moving. So it starts out moving kind of slow, it speeds up, then it slows down again right here because the absolute value of the velocity is decreasing. But those entire 8 seconds, it's still moving to the right. And it's possible that at some point during those 8 seconds, the particle will cross through the coordinate 35 meters. I like to do it this way. First, just ask yourself, what is the area of one of these squares on the grid? You can see that the height of this square, 10 minus 5 would be, or 10 minus 5, that would be 5 meters per second. Those are the units associated with velocity. And the base of the square here is 2 minus 0, or 2 seconds. Now maybe you're thinking, first of all, is that even a square if it's 2 on one side and 5 on the other? Well, if you were making a graph with equal dimensions on both sides, I suppose that would not be a square. I'm just calling it a square because it's drawn as a square in the picture. Now, when you take 5 meters per second for the height of the square times 2 seconds for the base, you actually get units of 10 meters. And you may be thinking, that doesn't make sense because area should have units like square meters or square inches. Well, that's only true if you're multiplying distance by distance. We're multiplying a velocity by a time. So these really are the appropriate units, especially when you go back to the equation and remember that the area is supposed to give you displacement. And we know that displacement has units of meters. So now it's just a matter of counting up the area of triangles and squares until we get to 35. So between during the first 2 seconds, the area under the velocity curve is half of a square. Half of 10 would be 5. Did I put 10 down here? Yes. Each square is 10 meters. So the displacement during the first 2 seconds is 5 meters. And let's just, well, I could put that in equation form by saying 5 meters equals the initial position plus the area under the velocity curve during the first 2 seconds. And I think if you count here, you will see we've got 2 full squares. That's 10 plus 10 equals 20 meters of displacement. But then we've got 3 triangles on top of that. So 20 plus 5 plus 5 plus 5 again will give you a displacement of 35 meters. So during those first 6 seconds, the particle was moving to the right the entire time, and it covered a distance of 35 meters. So that's where it is at the time t equals 6 seconds. Now that's not the end of the answer, because if you read the problem carefully, they actually ask, at what time or times plural? So there may be another time. Now if we allow time to continue, you can see that during the next 2 seconds after 6 seconds, the particle will undergo another displacement of 5 meters. This is a positive triangle with area of 5. So it'll go from 35 meters to 40 meters, and this is right where the particle stops. How do I know that? Because that's where the velocity goes to 0. So the particle will stop at t equals 8 at 40 meters. Then its velocity becomes negative. So if the particle has come to a stop at 40 meters, now it's going to back up. And between 8 seconds and 10 seconds, you can see that the area is also 5 meters, but this time it's signed area, S-I-G-N. It's a negative area because it's on the opposite side of the t-axis. So it actually undergoes a displacement of 5 meters to the left. So if at 6 seconds it was already at 35 meters, during the next 2 seconds it moved another 5 meters to the right, which would put it at 40 meters, and then during the next 2 seconds after that it moved 5 meters to the left, which would put it back at 35 meters. So there's another answer to this problem. It's right here. The final coordinate of 35 would also be equal to the initial coordinate plus the area under the velocity curve between 0 and 10 seconds. It's covered up now, but this says 10 seconds. All right, so 2 answers to that problem. Now, 2 solutions to a problem. That may remind you of a quadratic equation. When you have a degree 2 polynomial that you set equal to 0 and you're looking for the roots, you can often find 2 real numbers as solutions. And we're going to see that that's really what's going on behind the scenes here. That's another way of thinking about this problem. So it is not necessary for you to do this. And I'm noticing up here I probably should have put 35 meters. I should have specified the units. You do not need to do it this way. I am not going to ask you to do this on an exam because this is not a math class. This is a physics class. We're not going to use too much math here. We are using math, but what you could do is actually find the functions that describe these lines and integrate them as you would in a calculus class. So let's look at this first line between 0 and 4 seconds. Do you see how the rise over the run would be a rise of 10 meters per second over a run of 4? And the intercept is the origin. So this actually is the equation of the line between 0 and 4 seconds. It's got a slope of 10/4 and an intercept of 0. And of course we can reduce 10/4 to 5/2. Between 4 seconds and 8 seconds, the slope is now the negative of the first slope. So it's got a slope of negative 5/2. And what's the intercept? Well, can you see that if you follow this back to the v-axis, you'd be up here? Follow this line back, and you'd wind up right here at 20 meters per second at t equals 0. That's how I knew that the intercept was 20. So this is the appropriate equation for the line between 4 and 8 seconds. Now, since we already know with the benefit of hindsight that one of the solutions is between 4 and 8 seconds, what I'd like to do now is actually compute the function for position between 4 and 8 seconds. So for any time between 4 and 8, let's find the formula that would give the position. And we know that we merely have to integrate. The final coordinate is the initial coordinate plus the area under the velocity curve between 0 and t seconds. And I've had to define that function piecewise here. This is the appropriate function during the first 4 seconds. This is the appropriate function during the seconds after t equals 4 seconds. And here I'm just going to go kind of quickly. You know how to integrate with the power rule. When I evaluate at my upper and lower limits of integration, I get this expression, which I can simplify. 20 plus 20 minus 80 would be negative 40. Here is the formula that I get. So as long as you're evaluating the position between 4 and 8 seconds, the x-coordinate should be given by this function of time. And as a check, we can plug in the time t equals 6 seconds. You can check for yourself if you'd like, but when I plug in 6, I find that the x-coordinate is 35. Or you could do it this way. You could set this equal to 0. I'm sorry, not 0. Set it equal to 35 and look for the solutions. That would amount to solving a quadratic equation. You would probably get 2 roots. You would definitely get 2 roots. One of them you would have to throw away because there's only one valid solution between 4 and 8 seconds. This function does not work. You know what, I take that back. It would work for, yeah, you know, I've said this only works for times between 4 and 8, but look, the function doesn't change anymore after that. It's this, over here, the velocity function is still given by this equation. So this would be valid anywhere after 4 seconds. And I think if you set this equal to 35, solve for the 2 roots, and you will likely find, I'm like 99.99% sure that you'll find the 2 roots 6 seconds and 10 seconds. Exercise number 32 from chapter 2. Yes, chapter 2. That's very similar to the previous problem. In this case, you're given a graph not of velocity versus time, but of acceleration versus time. And the first thing to note would be that the acceleration throughout the motion here is positive, which means that the velocity is always increasing. Now, that doesn't mean necessarily that you're speeding up. Remember, your velocity could already be negative. Let's say your velocity is negative 10 meters per second, so you're moving to the left. If your velocity is increasing, as it would be with a positive acceleration, perhaps your velocity goes from negative 10 to negative 8, because negative 8 is greater than negative 10. Well, a velocity of negative 8 is still in this direction, but it's slower. So I'm just reminding you that positive acceleration does not necessarily mean that you're slowing down, or excuse me, that you're speeding up. It could be either. Okay, in the problem, we're told that the particle starts from rest, which is just a colloquial way of saying that the initial velocity is 0. Now, if your velocity starts out 0 and you have a positive acceleration, when a velocity increases from 0, it will end up positive, and it will become greater. Well, it'll take on more and more positive values. So for this particular problem, we actually are speeding up the whole time. They would like to know what is the velocity at 6 seconds. So obviously, we're going to have to use the relation between velocity and acceleration. Hopefully, the first thing that pops to your mind is this. The time derivative of velocity is acceleration. That's easy to remember. Once you have written that, you can use your understanding of calculus to get to the next step. Clearly, if acceleration is a derivative of velocity, then velocity is an antiderivative of acceleration. We can use the fundamental theorem of calculus. if we would like to know the area under the acceleration curve between two times, just take an antiderivative of acceleration, which would be velocity, evaluate that at the two times, take the difference. Okay? Or you can just memorize change in velocity is the area under the acceleration curve. For many of you, that may be easier just to memorize that. Let's put the v initial on the other side. So given any initial time and then the area under the acceleration curve for some subsequent time interval, we can find the velocity at the end of that time. In this case, our initial velocity is 0. We're told that we start from rest. And that it's understood that our initial time is also 0. We can see that from the graph. And our final time here is obviously 6 seconds. So let's just adapt this equation for the present problem. We would like to know the velocity at 6 seconds. That should be the velocity at 0 seconds plus the area between 0 and 6 seconds underneath the acceleration curve. Now, just like the previous problem, if you wanted, you could use algebra to get the slope-intercept form, let's say, of these two lines and actually integrate those functions using the power rule to find the velocity at this time. But it's much easier just to use geometry. We know that the formula for the area of a triangle is 1/2 base times height. And here's where I plug in 0 for the velocity at 0 seconds, since we're told that we start from rest. So the area 1/2 times the base. Well, the base is these 6 seconds here. The height is 10 meters per second per second. Notice how the units work out. Meters per second squared times seconds does give us the appropriate units of meters per second. Well, 6 over 2 is 3. 3 times 10, there's our answer. We're going 30 meters per second at the end. Okay, we'll tack in a different direction with this next exercise, number 38. They tell you that you've got a block on a spring. This is something that gets talked about often in introductory mechanics. That's this class, by the way. A block on a spring, you pull it down from its equilibrium position, and then you release the block and look at a graph of its position versus time, its vertical coordinate. And you may not be surprised to discover that it looks something like this. Instead of a jagged sawtooth wave where it's just straight line, straight line, straight line, you've got these nice smooth corners as it gradually comes to a stop and then bounces back in the other direction. And that's what we're looking at here. This is a two-part problem, and in part A, they're asking a number of things. First of all, when is the velocity 0? When is the velocity positive? And also, when is it negative? Well, we know when we look at a graph of position versus time, we can extract information about the velocity function by looking at the slope. Typically, we've been using the letter x, but now we're talking about a vertical coordinate, which we tend to call y. So dy dt, the derivative of y with respect to time, would be the vertical velocity. And again, the derivative on a graph is merely the slope. So all we have to do is ask, when is the slope 0? That is when the velocity, or excuse me, the position's not changing. And by definition, that's a velocity of 0. So we can see here at 0 seconds, 1 second, 2 second, etc. Every integer, every second really, is when the slope is, just for a moment, 0, and that would mean that the velocity is 0. Think about it. If you're right here in the motion, a very small time, or a small, I don't want to say unit of time, but a fraction of a second later, just bump to the right just a little bit. Do you see how the y-coordinate has not changed? It's changing rapidly in here. Like if I'm right here and I move 1/10 of a second to the right, the y-coordinate has already decreased. So there's a noticeable change in position. But here, if I move 1/10 of a second to the right, the y-coordinate is practically the same. And that means it's not changing, which is another way of saying that the velocity is basically 0. That's when the block reaches the top of its oscillation and appears to kind of stop for a moment before it moves back down. It's kind of like what they call hang time, when you watch a basketball player jump up to dunk, and at the top of their jump, it almost looks like they're hovering for a moment because it takes time for gravity to accelerate them to a noticeable velocity. Okay, when is the velocity positive? Well, if velocity is the slope, all we have to do is look at when the slope is positive. So In here, the slope is positive. Notice that's where the y-coordinate is increasing. It's going from negative to positive. Here, the y-coordinate is decreasing, and that's a negative slope. Makes sense, right? If your position's increasing, you're moving to the right. That's a positive velocity. Over here, y-coordinate is increasing. That means, I shouldn't say moving to the right, because in this picture we're talking about up and down motion. So right in here, the y-coordinate is increasing. That means the block would be moving upwards. And I realize the graphic I chose here, darn it, just ignore this. They're choosing a different coordinate system where they say that down is positive. Let's forget about that. Let's just pretend that up is positive, so that when the block is moving in the upward direction, its y-coordinate would be increasing. That would correspond to this section right here. And then, of course, the third part of this part A, third part of part A, when is the velocity negative? I kind of already said that. That's where the slope is negative. Now, I want to go above and beyond, and since we know that the velocity is the derivative of position, if we had an actual function for this position versus time graph, we could take its derivative and answer the problem that way. They didn't give us a function, but you'll notice this looks a lot like sine function and or cosine. So let's continue with that thought. I've reproduced the graph here, and let me remind you, maybe on the back, the cosine function starts at 1, dives down to -1, dives back up, etc. That's cosine of t. And we know that the maximum value there is 1. Now, where does this happen? Doesn't cosine go to 0 at pi over 2? So this is pi over 2. This would actually be pi. And that means this would be 2 pi. This graph is not the same as the graph that we're given. It's actually it's like if you flip it across the t-axis, they are the same. Almost. The only difference is here, the zero slopes happen at 1 second, 2 seconds, 3 seconds. Here, the zero slopes happen at pi seconds, 2 pi seconds, etc. So I can make 2 modifications to the cosine of t to turn it into this function. Check it out. If I go y of t equals negative cosine of pi t, they didn't actually give us the height or amplitude of the function. Let's just pretend it's 1. This function does correctly describe the motion here because, well, let's just check. When t equals 0 seconds, that's right here. What's the cosine of 0? That's 1. The minus sign makes it -1, which puts us at the correct y-coordinate. What about at 1 second? If you plug in 1 second, the argument of your cosine function becomes pi times 1, which is 1. The cosine of pi is -1. -1 times -1 does give us +1. So this is the correct function for the motion that they've drawn. And now we can kind of cheat and just use the fact that the velocity in the y direction would be the time derivative. It's the instantaneous rate of change of the y-coordinate. And you guys know how to take this derivative, right? What's the derivative of cosine? That's negative sine. The minus sign will cancel this minus sign, so we get a positive sine of pi t. But don't forget, chain rule says we have to take the derivative of the inside with respect to t, and so we pick up a factor of pi out front. That just stretches the velocity curve. But we find that the velocity is proportional to sine of theta. So I'm going to draw the sine function down here, and I would like to make sure that it lines up with the one that's already drawn. So this is, I like to call this a quarter hump, and these two together would be a whole hump, or these two together. So one hump, no, not a quarter hump, a half hump. This is half a hump, this is one full hump. And it looks like every second these two sinusoids execute 2 half humps or a full hump. So the sine function should look like this. This is what I'm getting at. Okay, this is roughly vertical velocity versus time. So we could also answer part A of this problem by looking at the graph of the derivative of position. They asked, when is the velocity 0? Well, evidently, it goes to 0 here, here, etc. Every second, the velocity goes to 0. That's the same answer we got up here by looking at where the slope goes to 0. They'd like to know, when is the velocity positive? Well, it's positive between 0 and 1 second, 2 and 3 seconds. We would have arrived at the same conclusion by looking at the actual position versus time graph, because here we can see that the slope is positive in this time interval. The slope is positive in this time interval. In this time interval, the slope is negative, and we can also see that down here because the derivative of position, which is velocity, takes on negative y-coordinates. I really mean negative vertical values on the graph. Okay, so the same information that you can get from the position versus time graph, you can also get from the velocity versus time graph. Now, what are they asking us in the second part of the problem? Oh yeah, we've already done it. They asked us to sketch a reasonable function for the velocity. So you would have wound up with something like this anyway. By qualitatively, you would recognize, okay, in here I have to draw a function. Since the velocity is the derivative, which is graphically the slope, let's just analyze the slopes here. We see that they're all positive, and then the slope goes to 0. So you would have said, okay, the slope has to start at 0. See how the slope here is 0? The slope, which is velocity, starts at 0. It increases. See how the slope is gradually increasing? It reaches a maximum value at half a second, and then the slope starts to decrease. So you could just recognize the slope becomes positive. It peaks at half a second, and then the slope decreases back to 0. Slope is velocity. So you would recover a graph like this anyway. I just went one step further and found the precise function that describes the velocity. And now it's time for a spreadsheet problem. You don't have to do this in a spreadsheet, but I do like an excuse to use Excel. Again, this is one of those problems kind of like the Empire State Building problem that was likely written in 1950 because they need some fictional planet here. You're an astronaut, you're a space traveler, you've landed on a foreign planet called Planet X. Well, as of what, 2005, 2010, no, later than that, more like 2013. There's really no need to make up names like Planet X because astronomers have now confirmed the existence. Where's my, oh, I was looking for the laser pointer. This is not PowerPoint. Astronomers have confirmed thousands of so-called exoplanets, planets outside our solar system. In some instances, they actually have photographs, believe it or not. If you Google it, Google Keck telescope exoplanet, you can find infrared images of planets very far away around a different host star than our own. So there's no need for Planet X. We've got actual planets. Of course, the names are not very creative. They're mostly like catalog names, Kepler 3b and such. Okay, so on this planet, you explore the strength of the free fall acceleration, and you do so by taking a heavy object and just dropping it from several different heights, and you time how long it takes to hit the ground. Now, in practical terms, this is really a terrible way to measure G. I know I've tried. And the reason is that your reaction time is comparable to the amount of time it takes the ball to hit the surface of the planet. Look here, if the fall time is 0.7, well, oftentimes, like if you want to press a button after you hear a beep, the delay between the actual beep, or hearing the beep, and pressing the button could be as much as 0.3 seconds. And 0.3 seconds is significant compared to 0.7. So your data would be pretty poor in real life if you did this experiment. You would need like a photo gate or some sort of equipment to more precisely time the fall. And we're supposed to turn this data into a value for G. So here I am in Windows 10's fancy split screen mode, and I should point out that I already recorded this part, but I forgot to capture the whole screen. I only recorded the web browser, so it was me talking about what I was doing in the spreadsheet, and you couldn't see the spreadsheet. So I'm re-recording that, and later in this video I will refer to that fact, so don't let that confuse you. Okay, I just need to get this data into my spreadsheet so that I can eventually plot it and do some other manipulations So I will start with column headings. Let's see, I'll use bold type. I will enter the height in meters. It's always good practice to include the units in the column heading so that you can just put numbers below and there's no need to specify the units. I need the fall time in seconds. All right. And rather than enter each of these times individually, what I can do is be smart about it and say, hey, Excel, I would like you in this next cell to take the previous number, or the previous time, so I'm hitting the equal sign and then watch what happens in the formula bar here. I click on the previous time and I say, please add 1 second to that previous time. I hit enter and it does that calculation. And now I would like Excel to iterate that calculation down to 5 seconds. So if I hover over the lower right corner, the white cross turns into a black cross, click and drag, and it automatically creates a column of times where each time is 1 second later than the previous. So if you look at the formula bar, as I'm scrolling, you can see how it enters the correct syntax in each cell. That's probably the most useful thing about Excel, or one of the most useful things. Now for the times, there's no pattern there. I have to enter these manually. And you'll notice that they've forced the data to include 0, 0. You can't actually drop something from a height of 0 and record a time of 0, can you? But we know, according to the theory, that should be one of the data points. So all I'm doing is transcribing the numbers here. And now that we've got the data into the spreadsheet, we can do some stuff with it. On this planet, Planet X, here's the surface, let's say, and you've got your setup. Maybe, so here's you as the astronaut, and you're always going to drop your object from the same height. That's sloppy. No, that's not correct. You drop it from different heights. What am I doing? So here's your variable height, h. We need to choose a coordinate system. Let's call up the positive y direction. Here's positive x. So because I've put the origin here, it's understood that the surface of the planet is at a y coordinate of 0. So all of our y coordinates will be positive as they fall. And we're trying to find the acceleration. So for each of these trials, you've got a given height through which it falls, which is really displacement, is it not? It's a change in y coordinate. Well, in each case, we know that the initial velocity is 0 because the object is dropped from rest. And we've got a time interval. That was in the spreadsheet. And we'd like to find the acceleration. So hopefully you immediately recognize there is an equation we've been dealing with that connects all of these. It's this one. Displacement equals v naught delta t plus 1/2 a delta t squared. We know this quantity. For each trial, we know the distance that the rock fell through, and we know the time interval. We know the initial velocity is 0. So we're really just dealing with this. This is easy. Now, if you drop something through a height h, you could say it's final. It's here. Delta y is y final minus y initial, which would be a final coordinate of 0 minus an initial y coordinate of h, the height. The short way to see this is just the displacement is downwards through a height h, so it's negative h. The negative comes from the fact that the displacement is downwards, but we're calling up positive. Now the acceleration, by definition, is the free fall acceleration with a minus sign. Remember, in this class we use the letter g to mean the absolute value of the free fall acceleration, but because of our choice of coordinate system, the acceleration must have a negative value. So here we go, negative h equals 1/2 times negative g times the time interval squared. Of course the minus signs cancel, and this is our equation, g delta t squared. So you can see here that for each trial individually, we could plug in the height through which the rock was dropped. We could plug in how long it takes for the fall and solve for g. G would be 2 times the height over the square of the time interval. And you've probably, that probably looks familiar to you at this point. So what I could do is go back to the spreadsheet, and for each row, I could have a third column, and in each row I could calculate the g based on the data from that one trial. And I will do that. That's not a bad way to go. But it turns out there's a better way to do it, because since we did, what, 6 trials, I think it was, we could calculate g for each trial and then average them and get some average value for g. That's fine, but mathematically, or statistically, there's supposed to be a better way of doing it called a method of least squares. So I'm going to put a box around height and a box around the square of the time. Notice if I were to graph h versus time interval, there's a quadratic dependence, right? Doesn't h depend on the square of the time interval? So if I were to graph height versus delta t, it should be quadratic. If we were to plot the data points, we should have something that looks like a parabola. It would be nice if we could plot a line, because once you've plotted a line, even if you were doing this by hand, you could use a ruler to draw what's called a best fit line. So I've put a box around the square of delta t. Now think of this kind of like a y coordinate if you're back in high school algebra, and this is like an x coordinate, and then this quantity here would be like m. And what you see is this quantity is proportional to this quantity. That's like y equals mx. And we know that this graphs as a line that goes through the origin, because there's no y-intercept. In other words, if we plot height versus the square of the time interval, according to the theory, that equation that we just wrote down, delta t squared, those points should fall on a line, because according to the theory, they are proportional. And I'm not putting the dots directly on the line because I'm allowing for the fact that there's going to be some measurement error. So in the spreadsheet, I would like to make a plot of height versus the square of the time, and that plot should look like a line. It should be close to the line. Now, since the slope is 1/2 times g, g would just be 2 times the slope. That's what we're doing here. So we can ask Excel to plot the best fit line through our various data points, determine the slope, we'll get the slope from Excel, and then we can just double that and use that as our best value for the free fall acceleration. So the idea is on this graph here, see how this point's a little on the high side, it's above the line, this point's below the line, this one's a little bit above. So I didn't draw the very best fit line here, but the idea with the best fit line is some of the errors are on the high side, some are on the low. It's a compromise. And from what I understand, you can use statistics, that formidable branch of math called statistics, to show that the slope here would be a more representative value of the true free fall acceleration than merely calculating the g's for each trial and then averaging them. Let's do both, though. We'll go back to the spreadsheet and implement both methods. You know, I just realized that previously when I was sharing the screen, I think I was only sharing the web browser, not the whole screen. So I don't even know if you saw the spreadsheet. So I'll have to go back and fix that. Now, if I did already fix it as you're watching it, now you're wondering what I'm talking about. This is like Inception. Let me just move forward. Okay, so now I know you can see my entire screen here. Let's go ahead and calculate g one way. I'll say g in meters per second. And if you look back at what I just wrote, we found that g was 2 times the height divided by the square of the time interval. So I'm going to enter a formula here. This is equal to 2 times the height divided by the square. So I'll click on the cell for time, and then I'll square it, raised to the second power. And before I hit enter, I know there's going to be a problem here because we're actually dividing by 0. The table includes the data set or the data point 0, comma 0. We know that if you were to drop something from a height of 0, it would take 0 seconds to get to the ground. You wouldn't actually do that trial, of course, but according to the theory, that also belongs in the data set. And that helps force your line through the origin. But Excel doesn't like it when you divide by 0. So, see that? I'm just going to ignore that. But you know, this little pesky thing irritates me. So, how about I enter the formula here instead? I'll say equals 2 times the height divided by the square of the time interval. I'll hit enter. Oh, great. And now here's where I can hover over the lower right corner. When you see that black cross, you can double click and it will go ahead and repeat that calculation all the way down. So the spreadsheet is smart. If I click on this cell, it knows that to calculate this value for G, it should use this height and this time. You can check the formula here. And it is referring to the appropriate cells. In fact, as I go up the cells, you can see up here, you can see how all the numbers immediately update as they should. Now, we don't need all these digits. This is silly. So I'm going to select all of these. Whoops. Control Z. What is this? Cancel. When you select this whole block, and there's a button here, I can decrease the number of digits shown. Let's just go with 2 digits because, or 3, because these numbers have only 3 digits. That ought to be fine. And now I can say, okay, G average. And in this cell, I would like to take the average of these 5 values for G. So I'll say equals average, open parentheses, and then I highlight all of these cells. Okay, so evidently the gravitational acceleration on this planet is a little weaker than it is on planet Earth. Let's try the other method now. I showed that on a plot of height versus the square of the time, the slope would be equal to 1/2 G. So I need to insert another column here, and I'll say time squared, fall time squared, and that units would of course be seconds squared. And to do that, that's easy. I say equals, take the time and square it. And that's okay for 0. 0 times 0 is not undefined. So double click, there we go. So now I've got a column for the heights and a column for the squares of the times. Here's a technique you are going to use repeatedly this semester for some of your labs. Let's go up to insert. I would like to insert a scatter chart. Click on this drop-down menu. See, these are the scatter charts specifically. I do not want to connect the dots. Usually we'll just do this simple scatter plot, no connecting the dots. Now, Excel is really presumptuous. It thinks it knows what you want to plot. It does not know what I want to plot. So I need to right-click on one of these data points, go to Select Data, and see, it's already made some assumptions about the data series that it thinks I would like to plot. Let me just get rid of all this garbage. And now I would like to add a data series. First, I'll give it a name, height versus t squared. Now, they're referring to the air quotes x values. They really just mean the abscissas, the coordinates that you would like to be plotted horizontally. For us, that's actually the square of the times. We want to plot height versus time squared. So I'm going to grab, I'll click, and I'm holding down shift, I'm hitting the arrows. I'm going to grab all of those time squareds. Wait a minute. How many were there? 1, 2, 3, 4, 5. I can't see. Yeah, that's all of them. Okay, and then I like to hit tab to get out of that field. And then I still don't know what this equals 1 in brackets is. Just delete that. For the quote, air quotes, y values, that's actually our heights. That's the vertical coordinate on the graph. So I'll click here and scroll all the way down. You really should hit tab again, because sometimes if you don't, it doesn't actually collect, it doesn't enter what you type. So hit OK, hit OK again. Great. Now these points do in fact look like they fall on a line. Let's now ask Excel for a best fit line. So there's a couple ways to do it. I think you can do it from this menu, plus We can add a trend line. Yeah, you could do it that way, but I'm going to do it the old school way. Let me hit escape. If I right click on a data point down here, you can also do it here, add trend line. And then some options pop up. So you could actually do a best fit quadratic function, cubic, polynomial, even a logarithmic function, but we just want a line. So I'll leave it linear. Now set intercept. Yes, we do want to force the intercept to be 0. Actually, we don't need to do that. Or do we? We've got 0, 0 included in our data, but we still want the line to go through the origin. So I think we should select that option. And then since I'm interested in the slope, I want Excel to display the equation so that I can get the slope from the equation. Okay, now notice how the equation they've given has an intercept of 0. Let me scoot this over. And I'll make this bigger so we can read it. I'll change the font to something like that. And instead of y versus x, we know that we're really plotting height versus the square of the time. All right, and the slope there, of course, is this number out front, 3.727. So let me make this smaller now so I can see my spreadsheet again. And down here I'll say slope of graph. I guess I can put that value here. 3.7273. And if you rewind or think back to what I was writing on the paper, we determined that the free fall acceleration should be 2 times the slope. So I'll say g graphical, my value of g from the, or I could do this, best fit. My value of g as determined from the best fit graph. And really I should probably put the units here, but since I've already specified the units in this column and I'm putting everything in this column, that kind of works. So this would be equal to 2 times the slope. So I click on the cell for slope, and there we go. 7.45 is not the same as 7.39. Like I said, you can use statistics to make the case that this is really the better value for the free fall acceleration. This technique will get used again this semester. So we don't do anything too fancy with Excel. Most of the features that we will use, you've already seen them here in this example. Last one here, number 49 from chapter 2. This is the deer in the headlights problem. You're out, you're cruising in your car one night, maybe through the woods. You're going 20 meters per second. That's maybe 45 miles an hour. And you see a deer step onto the highway. Fortunately, the deer is quite a ways ahead of you. Let's hope you have time to react, brake, and bring your vehicle to a stop. Now, they tell us that it's going to be a full half second between seeing the deer and actually hitting the brakes. You know, you need that half second to swear, react, get your foot on the pedal. But after a half second, you are now slowing down at this rate, 10 meters per second. So you're pulling a full G. I guess what that means is a car can accelerate to a stop. Most cars can accelerate to a stop more quickly than they can get up to speed. Even if your car can't accelerate at 1 G the way a Porsche might be able to do, or I don't know, some real sports car, your car can accelerate perhaps at 1 G using the brakes. So brakes are pretty effective for accelerating. They just make you slow down, they don't make you speed up. Okay, we're supposed to figure out how much distance is between you and the deer when you come to a stop. See how optimistically they phrase this problem? You just get to assume at the outset that you do not hit the deer, because that would be a sad story. Let's try to solve this a couple ways. We'll do it graphically first, and then we'll set things up very carefully the way the solutions manual does. Here's my super elaborate picture. We need a coordinate system, and so far we've specified the truck is going towards the deer. It's got this initial velocity. How about we put the origin at the very front bumper of the car, which is convenient because what matters is that the bumper not touch the deer. We're also told in the problem that at the moment you I'm trying to say spot the deer, it's 35 meters from the front of the car. And even though I've drawn a y-axis here, this problem takes place entirely in the x-axis. Okay, nothing left to see there. Let's get to work on paper. How about we start with a plot of velocity versus time? Because we know that the area under velocity versus time will give us displacement, and that's what we're looking for. We'd like to know how far the truck moves before it comes to a stop. So this is just a qualitative graph, velocity versus time. We know that the car drives for a full half second at its initial speed before slowing down. So let me draw that part of the motion. That's just going to be constant velocity, in other words, zero acceleration at 20 meters per second. And then at that half second mark, 0.5 seconds, that's when the car begins to slow down until some final time, which we don't actually know yet. Perhaps we could solve for that time, but we're not really interested in that time per se. We'd like to know the area under the curve, because displacement is the area under the velocity curve. Of course, you'd have to choose time limits that correspond to the final and initial position there. Now, what we are told is that the acceleration during this part of the motion is 10 meters per second per second. That's really the magnitude of the acceleration, because if the car was moving to the right, the acceleration would actually be negative. So let me say this. The slope here, we know that the slope of v versus t is acceleration. The slope is 10 meters per second per second. So I think you can do this in your head. If you start out at 20 and you're slowing down at 10 meters per second every second, how many seconds is it going to take to come to a stop? Wouldn't this just have to be 2 seconds of time? You start at 20 meters per second. If you're slowing down at this rate, then after 1 second, you're now going 20 minus 10 is 10 meters per second. Slow down by another 10, you're back down to 0. So this would be 2.5 seconds. So we have already answered the question, at what time does the truck come to a stop? But what we really want is the area under the curve. So let me just say this. Delta x, which I guess I'm defining as, maybe we should define some times here. T naught is when you see the deer. T1 equals, and I should really call that 0 seconds. T1 equals half a second. Hit the brakes. And at time T2, the truck stops. Those are the relevant times here. T0, T1, and T2. Okay, so delta x, the delta x that I guess what I'm doing is this. Delta x total would be x1 minus x naught plus x2 minus x1. There we go. I've broken the displacement up into 2 separate contributions. This is the displacement during the acceleration. That would be the area of the triangle. This is the displacement during the initial half second when you have not yet hit the brakes. And you'll notice, doesn't the x1 here with the minus sign cancel that x1? And what we're left with is x2 minus x naught, which is the total displacement. Now the reason I've written it this way is because the acceleration is constant during this interval. In fact, the acceleration is 0, and the acceleration is constant during this interval. It's the 10 meters per second per second. We can only use our constant acceleration kinematic equations during an interval for which the acceleration is constant. So you can't get away with using the 1/2 at squared term just once for the entire motion, because the acceleration is obviously changing. See how the slope is changing? Slope is acceleration. So we have to break it into parts. The acceleration is constant in here, and it's constant in here. So we can apply our constant acceleration kinematics separately to those 2 phases of the motion. Okay, well I know I'm just doing a rectangle plus a triangle. The rectangle's area would be the 20 meters per second times the half second. And the triangle's area would be 1/2 base times height. So 1/2 times the base of 2.5 seconds minus half a second times a height of 10 meters per second per second. Well, this contribution comes out to 10 meters. So the car moves 10 meters before the person has a chance to react. Remember, the deer starts 35 meters from the front bumper. So during that half second, they've already moved 10 meters closer. Now the deer is only 25 meters away. That's got to be a lot scarier than having a deer 35 meters away. But because we immediately slow down here, what's that last displacement? 2.5 minus a half is 2 seconds. 2 times a half is 1. So we really only go another 10. Did I do that right? Another 10 meters. I don't think I did that right, because I know the answer, and that wasn't it. So what have I done wrong here? 1/2. Oh, I see. The height. What was I doing? Not 10, that's 20. The height of the triangle is 20 meters per second per second. I almost prevented myself from embarrassing myself. So plus 20 meters. The total displacement is 30 meters. So I could say distance to the deer would be, how about I just do this, the absolute value of the deer's coordinate, because the deer is not moving, minus the final coordinate of the truck, which I'm calling x2, right, because of the labels for the times. So that would be 35 meters is where the deer is, minus the 30 meters for where the truck stops. And you've still got a good 5 meters to go. Close enough to see the fear on that poor deer's face, but then I guess it'll just walk unharmed into the woods. Let's do this a little more formally now. I can still keep the same setup. Let's do this. 0 is less than or equal to t is less than or equal to half a second. So during that first phase of the motion, I'd like to find out where the car is after the first half second. So I'll say I'm using delta x equals v naught t plus 1/2 a delta t squared. And right now the displacement is the position at time 1 minus the position at time 0. This is when you first hit the brakes. This is when you first see the deer. This is the velocity at the beginning of that time interval, which is the 20 meters per second. And the time interval is t1 minus t naught. And then I can just say 0, because during that first half second, the truck has not hit the brakes yet. It's not accelerating. Right, and solve this for, you know what, how about I just leave it? Okay, fine. I'll solve for x1. It's x naught plus v naught times the time interval. And because of our choice of origin, remember, I put the origin at the truck's front bumper at time t0. So its initial coordinate is actually 0. It's driving at 20 meters per second initially, and it goes for half a second, right? 0.5 seconds minus 0 seconds. And of course we get the same answer that we got before. 20 times a half is 10 meters. So this is where it is compared to its starting point when the truck driver first saw the deer. And now we can look at the second phase. So between half a second and I'll just say final time, which is t2, because we don't actually know what that time is. I'm still using this equation, but now it's position 2 minus position 1 equals, now be careful, the initial velocity for this time interval should actually be called v1. Plus 1/2 times the acceleration during this time interval, t2 minus t1 squared. And now we run into a difficulty, because we do know this quantity. We just found that after the first half second, the car has moved forward to the 10 meter mark. We're looking for x2. That's really what the question is asking us for. We know this because, remember, at the end of the half second, they're still going 20 meters per second. So this is their velocity still at the beginning of the next time interval, they will immediately slow down, but they're still going 20 at the beginning of this time interval. The problem is we don't know this time yet. Yes, I was able to get that graphically, but pretend we don't know that. We're solving this problem a different way. So this is another example of where we're using an equation that involves time or time interval, and we don't actually need the time interval. So can we try a different equation? What's the one that doesn't involve time? Remember this one? We've got final velocity squared minus initial velocity squared equals 2a delta x. The v squared equation. This only requires knowing the acceleration, which we do know. It's the 10 meters per second, and the initial and final velocities. Well, we know that we start out going 20, and we know that we come to a stop where the velocity is 0. So this equation is perfect. This will get us to the answer we want. So let me solve this for delta x, and I'll write it this way. x2 minus x1 is equal to, the times I'm dealing with right now, remember, are when you start braking and when you come to a stop. So 1 and 2. v2 squared minus v1 squared over 2 times the acceleration. And it's understood. This is your acceleration between these two times. What's our velocity at time 2? The whole point is to come to a stop so we don't hit the deer. So it's negative 20 meters per second squared. And downstairs, here's where you want to be observant of sign. Remember, the car is driving to the right, but slowing down. If you're slowing down, your acceleration has the opposite sign from your velocity. So it's an acceleration of negative 10 meters per second. And, well, don't we have a 20 squared over 20, which is just 20. So x2, let me put the x1 on the other side now. x2 would be x1 plus an additional 20 meters. We already found that x1 was 10 meters, and there's our 30 meters. So of course, we get the same answer that way. I kind of liked the graphical version better. For part B of the problem, they're asking, okay, what if you don't actually know your starting speed? Pretend you're not going 20 meters per second. What's the fastest that you could be going and still barely come to a stop without hitting that deer? And that reminds me of various funny movies I've seen over the years. I think I'm thinking of Home Alone, where Harry and Marv hit the brakes on that van right before they collide with Macaulay Culkin. He's walking home with his garbage bags. See, if I had a better editing program for these videos, I would go back and be playing that right now as I'm talking here. But anyway, he screams right before the bumper hits him. Classic scene. So if we don't know the speed, I think what we can do is just repeat this procedure, but now the velocity will be an unknown. And what is known is the final coordinate. So we found in this instance that the final coordinate was 30, meaning there's another 5 meters left over before striking the deer. Now we're going to assume that we just barely stop before hitting the deer. So the final x-coordinate is what's known. It's 35. This part of the problem is definitely a little trickier. Sometimes it's not obvious what the way forward is. And so you just have to start writing the equations you have to work with, plugging in the variables that you know, and trusting that it's going to head somewhere. Very often after you've written those equations, you'll start to see how to proceed. So let's work backwards now. Let me put the quantities that are given. The acceleration in that second part of the motion is still the 10 meters per second because your ability to brake has not changed, but your final x-coordinate at the time that I call time 2 is going to be the 35 meters. You stop right on the dime next to the deer. x1 is unknown because we don't actually know what that max possible speed is, so we don't know where they're going to end up at the end of the half second. The reaction time presumably has not changed. So the velocity at time 0, that's the same as the velocity at time 1. That's unknown. Let's call that V max, as your solutions manual does. Is that all we know? I think that's all we know. Well, we can also say this, T1 minus T0, that's still the half second of reaction time. Okay, well, we already saw that it was best to use the V squared equation for the time interval from T1 to T2. So let's do that again. And we'll say Velocity at time 2 squared minus the velocity at time 1. But remember, if the velocity at time 1 is same as the starting velocity, which is what we don't know. We're trying to answer the question, what's the fastest that you can be going and still be able to stop barely in time? So minus v max squared equals 2 times the known acceleration times x2 minus x1. Now, we do know x2. The whole idea is we're going to stop at 35 meters. We do not know x1. We also know v2 because we come to a stop. So this equation has one unknown, two unknowns. We cannot solve this single equation for the unknown that we're interested in because there are actually two unknowns. So can we perhaps determine this from the first part of the motion? Let's try that. In the first part of the motion, we know that the displacement, let's see here. Yeah, x1 minus x0, and of course x0 is just the origin. Well, that's the velocity at time 0 times t1 minus t0. I don't need the 1/2 a delta t squared term because we're not accelerating during the first half second. So this number is a half second. This is actually v max, is it not? That's what we're looking for. So I'm going to rewrite this equation crossing out x naught because that's the origin, and x1 is just the unknown max speed times that half second. I should probably have the 0.5 in front so it's easier to interpret. Okay, so now we can take this expression for x1. We don't actually know what x1 is. We don't know where the car is when the person first hits the brakes, but we can at least express it in terms of the unknown max speed. And I'll plug that in here. So we've got negative, I'm rewriting this equation now, negative v max squared equals 2 times, don't forget the acceleration is negative 10. And now for the displacement, the final coordinate is going to be 35, and the coordinate at time 1 we've seen is 0.5 times v max. So it looks to me like we have a quadratic equation in v max. Let's go ahead and distribute. I'm going to divide the whole equation by -1. So I find v max squared equals, well, we got rid of the minus sign, so this is now the number 20. 20 times 35, well, 2 times 35 is 70, so I think it's 700. And then we've got, don't forget, this minus sign is gone now. 2 times a half is 1. So this should be plus, I'm sorry, minus, because that minus sign is still there, minus 10 v max. Let me put this in standard form. V max minus 700 equals 0. And I am totally going to cheat here and just go use some online calculator for the quadratic formula. You know the formula, right? Vmax is equal to negative b plus or minus the square root of the discriminant, b squared minus 4ac, all over 2a. Well, here, a, that's the coefficient of the quadratic term, that's just 1. B is the coefficient of the linear term, or v to the first power, so that's 10, and c is negative 700. So I will go to the web and plug these numbers in rather than use a hand calculator. So I just typed in something like quadratic formula calculator. This is the first site that came up. This guy looks happy. He's happy that he doesn't have to do the quadratic formula by hand. So I enter a value of 1 for the coefficient that we call a, 10 for b, and negative 700 for c. And according to the results, well, we'd like something in decimal form here. They're calling it x. We know that x really represents the Vmax. So we've got two possible values for Vmax. One of them is negative. That doesn't make any sense, right? The max possible velocity you could have would be some negative number. That would put the car going the other way. So that's not physically meaningful. I will instead go with that last result and write Vmax equals, let's round that to 21.9 meters per second. Now think about it. The original problem had the car going 20 meters per second, and they were able to stop with 5 meters to spare. So it does seem reasonable that if you're going basically 2 meters per second faster, you're going to close that gap at the end. So that's a good example of a problem. These ads are distracting here. How do I stop sharing? That's a good example of a problem that requires repeated use of the kinematic equations. It requires you to break the problem into separate intervals over which the acceleration is constant. Because the acceleration is obviously not constant for the entire thing. We cannot apply constant acceleration kinematic equations to the entire time interval because they're not applicable. That's kind of circular logic there, but what we can do is break the motion into intervals over which the acceleration is constant, and then we can apply our equations. Look out for deers in the woods, folks.